Hello everybody, this will be the lecture for last Thursday that I missed, and I hope you're having a nice spring break. So this will even improve your grade, this lecture, I'm hoping. I will do some review of Galois theory, and then we will apply Galois theory to prime decomposition in number fields. Review of Galois theory. So suppose you have a field K, and suppose you have a polynomial which we will assume is irreducible, fx, and then you have another field which is obtained by adjoining the root of this polynomial to k. So this you can think of as k alpha, and f alpha is 0. The map here is, of course, the usual quotient map. So you take any polynomial in kx, you compute its residue modulo fx, that is an ideal, and then you send a given polynomial to its residue, and then whatever x goes to, that's alpha. So the map here, you compute g goes to g mod f, and then alpha is the image of x. So then you're essentially computing f mod f, and you get 0. So that's a root. If the degree of f is n, the degree of f is n, then this extension Lk will have degree n. All right. We will assume that K is a subfield of complex numbers. K is a subfield of complex numbers. This simplifies some of the technical details. For example, if the characteristic of K is positive, then this polynomial might be irreducible but non-separable. And then there are some complications that arise in the statements of main theorems of Galois. So we will not deal with it since number fields have characteristic 0. And now, having all of this, we have embeddings of L. So we have embeddings every embedding K into C extends to exactly n different embeddings of L into C, which fix K pointwise. So this is a fact from field theory, abstract algebra, and we already essentially at the beginning, when I assumed K is a subfield of C, I kind of fixed one of these embeddings. So then we have these n different embeddings of L into C, right? And now you say that L is normal. L is normal. this case it's the same as Galois. If any embedding L into C has the same image. Alright, so let's think about what this means. The polynomial, so let me erase this part. The polynomial, this fx, splits into linear factors. Okay, and then these roots of the polynomial are algebraically indistinguishable. So essentially, what you're doing in each of these embeddings is specifying one of these roots. So you're choosing a root, and then you're sending x to that root. So if you're imagining L as an abstract field, fx, then these embeddings are given by x going to alpha I. Alright, so then if all of these embeddings have the same image, it means that L, whatever it is, has to contain all the roots, because no matter which root you specify, it already lies in that image that you chose. So this assumption is the same. So this is equivalent to saying that L is the splitting field of some polynomial. And then using these embeddings, if you consider some other polynomial which has a root in L, then you can see that the fact that you're assuming all the images are the same, you get this strange fact that no matter what polynomial you choose, which has a root in L, then that polynomial has to split completely. Essentially by the fact that if you're applying these embeddings, now what happens to the roots of that specified polynomial, they get sent to each other, and then you have to have all the roots of that polynomial to be in L. Alright. So all these embeddings, if you're fixing some, assuming that we fixed an embedding of K into C, then all these embeddings are just automorphisms of L. So they move the elements of L around, but they are fixing the elements of K. So then, assuming this, you get another condition. So this is equivalent to saying that automorphisms of L that fix K, the number of those is equal to the degree. So this is part of Galois theory. It's not a difficult fact to prove, because the fact that you're assuming that your irreducible polynomial has all its roots inside of L, then all these embeddings correspond to choosing one of the roots, and then the embeddings are just the automorphisms group. They are identified with the automorphism group, so you get this equality. The number of automorphisms has to be the degree. All right. So an easy example of a normal or Galois extension is example q square root of 2. This is normal, right? So the polynomial that we're considering is x squared minus 2, and the other root is just the negative of the square root. And then if you take cube root of 2, this is not normal. This is normal, and this is not normal. Because the other two roots, the polynomial here is this one, and then the roots are cube root of 2, and then omega cube root of 2 omega squared cube root of 2, where this is the primitive third root of 1. Now, an easy way to see that this is not normal is to observe that this field is real. So it can be embedded into the real numbers, but omega is a complex number. So this root and this root are not in this field. Alright. Now if you start with a polynomial, you can always produce a Galois extension by joining all the roots of that polynomial. So say you started with this fx, right? This was over k, and then we moved to L by joining. So then we joined one of the roots, and then this f will in principle split. So fx will have x minus alpha 1 gx. If this gx is again irreducible, you apply the same construction, but now with this field, with L, and then you adjoin another root, and then you continue until you have done this enough so that your field finally contains all the roots, and this is the smallest normal extension, or the smallest Galois extension of K, which contains all the roots of F. So this is the splitting field of F. Alright, now from what I said about the embeddings and the relationship between the embeddings and the roots, it's clear that Galois group, so this Galois group of L over K, assuming L is normal, or Galois over K, then this Galois group is a subgroup, is naturally a subgroup of permutation group. Group of the roots, of the set of roots. And this group is, of course, is Sn, so is the permutation group. This I was denoting by automorphisms of Lk, is the same thing as, in this case, just being the Galois group. Okay, so this notation is interchangeable. You will see in some textbooks Galois group appearing even if L is not Galois, but whenever I write Galois, I implicitly assume that L is actually Galois over K. Alright. So how large is this group? Well, it's a subgroup of Sn, right? So and gamma Lk, the subgroup of Sn, N is often and equality often, but not always. So instead of continuing kind of the formal, a string of formal definitions and theorems, it's much more instructive just to look at some examples carefully. And if you understand these examples, you should be able to get the gist of what this beautiful theory is about. So here's a instructive example. So we will take fx to be x cubed plus 2, and I will denote by alpha this cube root of 2. Right, so then the roots are alpha, omega alpha, and omega squared alpha, where omega cube is 1. Okay, so there are 3 distinct roots, and the field that I'm considering this over is Q. So this is Q alpha, omega squared alpha. Now you can easily see that I can, if I take these 2 elements, alpha and omega alpha, I can divide this one by alpha, and then omega will be in this field. So this field contains omega. But if your field contains alpha and omega, then it already contains, then it also contains these 3 elements. So in fact, this field is the same as this field. Okay, so we will concentrate on understanding what are the automorphisms of this field over Q, which fix all the elements of Q. All right, so so one automorphism will be this going to omega squared and tau acting on alpha by not doing anything. Right, so let's make sure that this is actually an automorphism of this field. One thing that should be true is that every root goes to another root, and you can easily see that if you apply tau to alpha, then it goes here. If you apply tau to this element, it goes here. But what happens here? So if you're applying tau to omega squared alpha, right, so this is tau omega squared alpha, and this is actually what I said is wrong. So when you apply tau to alpha, it remains alpha, of course. It doesn't move to this root. So this goes to here. But if you apply tau to this element, then this is omega fourth alpha, which is omega alpha. So it's simply a permutation of these 2 roots. This tau flips these 2 roots. Now another automorphism which you can check is is actually an automorphism is this sigma, which now preserves omega. It doesn't do anything on omega, but on alpha it actually maps this to omega alpha. So now this automorphism of the field, it sends alpha to this root, and if you repeat this again, you will end up with this root, sigma omega alpha. This is sigma omega, sigma alpha, and this is sigma, well, this is omega, and then omega alpha, so this is omega squared alpha. And if you do this one more time, you will get omega cube alpha. So it's actually a triple, it's a cycle which sends alpha to omega alpha, this goes to omega squared alpha, and this comes back to alpha. Right, so we have two elements which it's not hard to check that these are actually automorphisms of this field. Maybe if you want to check all the details, then it's a bit tedious, but you should do it if you haven't seen this type of example. But we know that the number of automorphisms of my field, of the field that we're considering, this K, so this will be my L, or from this inclusion, let me erase this. The order of the Galois group of L over Q is at most 6, which is the order of the permutation group on 3 elements. And now I've produced two different automorphisms, this tau and sigma, and you can see that, well, then as you can easily see that you get the whole group, but just to make sure that we can see how these elements commute with each other, and to see this S3 appearing from the relationships is to maybe compute sigma tau. If you compute its action on alpha, you will get omega alpha. But if you compute tau sigma on alpha, you will get omega squared alpha. And then, so these two elements do not commute with each other. But you can check that tau sigma tau, if you do this, you will get sigma squared. So there is this relationship, and if you combine this with this being 1 and tau being of order 1, you can see that you're getting the generators of S3. So you're essentially getting the dihedral group because this relationship can be written as tau sigma tau inverse is equal to sigma inverse. Alright, so in this case you get S3. Now suppose instead of Here's another example, which we already encountered. If I take fx to be x5 minus 1, well, not this polynomial. If you want an irreducible polynomial, you should take the cyclotomic polynomial. Again, this is in Qx, so this is irreducible. Okay, and if we join one of the roots, this is omega 5 is 1, primitive its root, then you get an extension of degree 4. Every other root, right, because the roots of, so essentially what we're looking at are x5 minus 1, so there is this obvious root and then there's this fx, so every other root is a power of omega, so roots are omega, omega squared, omega cubed, omega 4, which means that when you join one of the roots, you already joined all of them. So this is in fact the Galois extension. Fx splits in Q omega. And now, which means that we have a group of order 4. Well, what is it? Again, you have this obvious automorphism which sends this to its square, right? And then you can apply this to other elements, and you will get how it acts on omega squared, omega cubed, omega 4. So the fact that this sigma is uniquely determined by its action on omega, it implies that you cannot randomly permute the roots. Okay, in the previous example, where we had 3 roots, what happens is that for each possible permutation of the roots, there is a Galois automorphism that does that. So all permutations are possible to see as automorphisms are produced by an automorphism of the field. In this case, this is not the case. So you cannot simply maybe switch these two and fix these other 2 roots. As a permutation, such a permutation exists, but it does not arise from the automorphism of the field. And this is an important point to understand, that not every permutation of these 4 roots arises in this case as an automorphism of the field, because there is an extra condition when you're looking at an automorphism of the field. So for example, if you're, say, moving these 2, you're moving omega to omega squared, then its value on omega squared is already determined. It's predetermined. You cannot obtain omega because this is a field, and you consider this as a product of omega with itself, and since this is an automorphism, this relation has to hold, and then you get omega squared, so you get omega 4. And then if you apply this one more time, you should be getting this element, I believe. So sigma omega cube. Here you get omega squared, omega squared, omega squared. So this is omega 6. And omega 5 is 1, so you get actually omega. So right. And then yeah, so okay, so then if you're applying it to omega 4, this will be omega by the same principle. You're getting 4 times 2, and you're getting omega cube. Yeah? Because 8 mod 5 is 3. So in fact what's happening here, if you draw the permutations, so this sigma sends omega to omega squared. Omega squared goes to omega 4, and then omega 4 goes to omega cube, and then omega cube goes to here. So this is how sigma acts. Alright, so it more or less should be clear that well, and you're allowed to send this omega to any other root, and that predetermines what happens on the other roots. So you have 4 possible elements, one being the trivial element, and the others being omega goes to omega squared, or omega goes to omega cube, omega goes to omega 4, and they are powers of each other. So in fact, the Galois group of this extension is isomorphic to the cyclic group Z mod 4. Alright. So let me erase this. Okay, so I will leave it as an exercise to compute a Galois group if you take this field. So you adjoin the square root of 2 and the square root of 3. Well, first find an irreducible polynomial. We did this in class, I think, that gives you this degree 4 extension. Okay, so there is a fx of degree 4. You should show that this is z2 cross z2. I find irreducible. Show that this is true, find the irreducible fx for which this field Q is a splitting field. And here, I mean, since we did this in class, you can consider this element and find its irreducible polynomial. You will see that it has degree 4, which means that the splitting field of that polynomial has to have at least degree 4. But this extension has degree 4, and it is obviously normal because it's a splitting field of x squared minus 2, x squared minus 3. So this is a normal extension which means that the degree 4 polynomial actually splits here. This is that strange fact that I mentioned, that if you have a normal extension, then any reducible polynomial that has a root in that extension will actually split completely. So, minimal polynomial of alpha has degree 4 and splits completely in Q square root of 2. It is the splitting field, essentially, of this polynomial. All right. And that's the exercise, and now the fundamental theorem of Galois theory So this gives bijection, one-to-one correspondence between subfields of a Galois extension and subgroups of the Galois group. So if you denote G to be the Galois group of L over K, then subfields of L that contain K, they are in one-to-one correspondence with subgroups of G. Okay, and the correspondence is that you take a subgroup H and you consider the fixed field of this H. So these are elements of L fixed by all elements of H. And this is in fact a subfield. This is even stronger in the following sense, that this extension, well, this LH, so let me erase this, L over LH is Galois. Is a Galois extension with Galois group LLH isomorphic to H. But LH doesn't have to be Galois over K. So LH over K is Galois if and only if H is normal in G. And in that case, the Galois group of LH over K, this is isomorphic to the quotient group. And here you simply take an element of G and restrict it to LH. Well, any element of LH acts trivially, so it's in the kernel, and then you get a map from G mod H, you get a map into this group, and the statement is that this is an isomorphism. Right, so this is one of the most beautiful theorems, in my opinion, in mathematics. I will definitely not prove this, but if you want to see a proof, and if you haven't seen a proof, then you can look up in any abstract algebra textbook. What I want to do is next is to consider more carefully the case of finite fields. Okay, so we will do the Galois theory over finite fields. I will then go back to a lecture before Thursday where we were looking at the splitting of primes in cyclotomic extensions. I will explain how the primes split. I did this already, but without sort of, maybe I was rushing a bit, and I had a feeling that not many of you, some of you didn't understand what I was saying. So I will explain it again slowly, and after that we will start doing the numbers. Right, so now I'll take a break.